Hello, everybody. My name is George Michailidis, and I'm a recent hire in the Department of Statistics. And I would like to take this opportunity to present my research interest and a little bit of background about myself. I got my undergraduate degree in economics from the University of Athens with a concentration in econometrics and operations research. And then I came to UCLA to complete my PhD in mathematics with an emphasis on optimization algorithms for multivariate statistical problems for my dissertation. After my PhD, I went to Stanford University, where I worked on problems in applied probability and stochastic control as a postdoc, and I acquired a different set of research interests that continue to this day. Before my recent joining the Department of Statistics at UCLA, I spent 17 years as a faculty member at the University of Michigan, followed by 8 years as a faculty member at the University of Florida, where my primary appointment was in the Department of Statistics, with secondary appointments in the Departments of Computer Science and Electrical Engineering. At the University of Florida, I was also fortunate to set up the Informatics Institute, and I directed it for 8 years. And the goal was to focus on research and training activities across campus on problems in data science and artificial intelligence. Finally, over my academic career, I have been very fortunate to work with a diverse group of PhD students and also mentor a fairly large number of postdocs. Turning my attention to research interests, they span a wide range and cover methodological aspects, theoretical issues, and also a diverse set of applications. And I have been fortunate to obtain funding throughout all these years from a number of government funding agencies, some private foundations, and also industry. Focusing a little bit on the methods and theory thrust of my research agenda, I would like to briefly discuss 5 areas where I have done work and I continue working on. A very big area for the last 15 years has been of what is known as high-dimensional statistics, whose characteristics is that the number of features or variables far exceeds the number of available samples, and that defines a different statistical paradigm than the more standard one, where you have more samples than variables. Within that big area, I have worked on different aspects, including model formulation, either from a more frequently stored Bayesian viewpoint, and particular topics that we looked at was for regression type of models, for graphical models, or for even more complex objects like networks or tensors. And once you have formulated the statistical model, you need to start thinking about obtaining good estimates of the model parameters, and that leads to problems in algorithm development and leveraging ideas from optimization. And once you obtain your estimates, then the question is, how good are they? And that leads to interesting questions regarding theoretical performance guarantees for the estimated parameters of your underlying statistical model. In many of these problems, the underlying assumption was that the data were independent and identically distributed, which is a very common theme in statistical modeling. But in many of these problems, my interest was primarily of what happens if the data exhibits temporal dependence or some network structure or heterogeneity where the identical distribution of the data assumption is violated. Finally, I was also interested, because of certain domains of application, on problems of data integration, where the features or the variables collected come from different domains, and it's much more useful and fruitful to break them into these domains and integrate them in an appropriate manner, because that provides more information to the subject matter experts. Another area that has occupied my research interest for the last 10 years has been broadly in problems in change point analysis and anomaly detection, where the key idea is to identify changes in the data generation mechanism. And I will show you a brief example towards the end of this presentation. And again, the issues I worked on were how to formulate the problem, develop algorithms, and also provide theoretical guarantees. Because of the rise of complex machine learning models over the last 15 to 20 years, and the fact that also we have a lot of data but cannot be stored in a single location, there has been a lot of recent interest in distributed optimization algorithms, where the goal is to have algorithms that obtain the solutions of the underlying statistical models while minimizing communication costs and achieve good performance. And the goal is not to have sharing data, which is very, very expensive, or in some cases, it is not even allowed because of privacy considerations. As I've alluded, since my postdoc days, I have a long interest in stochastic control problems, which primarily focus on, as you have flows through a network, how you have good scheduling or routing algorithms so that you optimize, for example, a metric of throughput or minimizing delays and related performance metrics. Finally, over the last few years, because of the rise of complex machine learning models and problems, I have been interested in the problem of attribution, which translates into identifying the key features that lead to particular predictions or outcomes by the underlying model, and therefore explain, in some sense, the particular predictions and the outcomes that the underlying machine learning model and algorithm make. Turning briefly to application areas, I have always been interested in the broad area of biomedical problems. Some particular topics include biomarker discovery for molecular data, where you have collected a lot of information or biomolecules like genes, proteins, and so forth. And the question is, which are the core ones that drive disease onset or disease progression? And more recently, I have looked at problems involving neuroimaging data. Given my training, undergraduate training in economics, I have always been interested in problems broadly in the areas of economics and finance, like systemic risk type of problems. And more recently, I was also involved in a bigger project where we had to develop a recommender system for an underlying intelligent tutoring platform and also test and assess its efficacy. Finally, I have been involved for a very long time in problems in computer and communication networks, and also power systems like the electric smart grid. I would like to give you a very brief flavor of some of the problems that I work on, and here are a couple of vignettes. One of them is on economics/finance, where the motivation was that because of the financial crisis, the goal was to identify critical institutions that represent potential weak links for the financial system. And what we did was develop the underlying methodology and also implement it. And here you see a brief outcome of how you monitor the level of risk at any particular point in time as captured by our methodology. And you can see that some of the, I highlight particular events that were significant as we found out. Another area is that relates sort of to change point analysis, but also network analysis is on problems in brain connectivity. The problem description is that given neuroimaging data, identify changes in network connectivity when the subject performed particular tasks. So for this data, the task that the subject had to repeatedly do was open their eyes for a certain period of time, then close them, then open them again, and so forth. And there are a whole bunch of other tasks that the subject may be asked to do. And as you can see, once these changes occurred, something changes in the composition, in the patterns in the data. Of course, Here, the patterns are fairly clear for this particular subject, and it's easy sort of to identify them visually, but we would like to develop fast and efficient algorithms that do that in an automated way, where things are not that visually obvious, and at the same time, they can scale up. So if we had hundreds of such objects, we can have much more an automated pipeline. So once you identify these change points, then you would like sort of to understand the network connectivity patterns. And here is sort of a picture of how the network of brain regions looks before the change, because here they had their eyes open and then they close their eyes, and therefore we see a switch in the network connectivity. So this was a brief introduction to my research interest and a little bit of background. I really like to work with students and tackle some of these problems. And I hope you will join UCLA and also join my research group. Thank you very much for your attention.